Okay, so what we're looking at here is question 4 of the Ray optics intergalactic problems. It deals with Fariah Jerry, which is one of the greatest intergalactic Christmas song singer extraordinaire in the intergalactic. You've probably heard of Fariah Jerry. If you're like, I haven't, you really have. Fariah Jerry is just amazing. And he has a quite striking jawline, and because of this, he likes to look at it quite often. Now, Fariah Jerry, when he's looking at an ornament on the classic lamppost of solitude, notices that when he is 20 centimeters away, and he knows that all of his ornaments have 10 centimeter diameters, he would like to see his image here, and he wants to see, where is this image? Is it real? Is it virtual and naturally uprighted or inverted? Because those go hand in hand. So we're just going to look at this ray optics problem and see where it takes us here. We know for our ornament, if here's the lamppost of solitude here in the wonderful world of the intergalactic, shining its light, a beacon of hope. And here is, the Christmas ornament on it. I don't know, a small lamppost, big ornament, whatever. We know this ornament is going to be a convex mirror here, especially if our eyeballs are on this side of it. Which means that we know that our focal point is behind the mirror and our center of curvature is back here too. Remember, everything behind the mirror, where there's not actually any light, has a negative quantity. So for our focal lengths and our distances, those are negative. Whereas we call in front of the mirror, where the light actually is, positive values. And one of the things we just need to be careful of here is that we know that the diameter of this spherical mirror is 10 centimeters. And remember, that's if I were to continue this all the way around. Well, if that's the actual ornament and that diameter is 10 centimeters, that means our radius, or the center of curvature, C, is 5 centimeters. And that means that the focal length, which is half of the radius of curvature, is 2.5 centimeters there. Okay, so we need to be careful there. Remember, the focal length is always the center of curvature over 2, or we can call that just the radius of that over 2. They're one and the same there. Okay, so we need to be careful about what we're using for our focal length. Our focal length in this case, right here, is 2.5 centimeters. Okay, so we can call F at the moment 2.5 centimeters. We're going to come back to that value of F momentarily, because we're going to see some stuff there that we might need to change. Okay. Now, if we create an object, and we'll just create this object anywhere on a convex mirror. If we know our properties of convex mirrors, we already know how this is going to pan out, but we can just kind of show it here. To draw our ray diagrams for a convex mirror, our first ray will come over, it will strike the mirror, and remember, when it strikes the mirror, it moves away from the mirror in such a way that if we were to backtrack this ray, it would pass right through that focal point. Okay, and I'm not the best drawer in the world, so let's just pretend I am for a second. Boop. Ding. And our second line that we can draw is a line that passes from the top of our object through the center of curvature. So we have this long line that comes down and passes right through it. Really what's happening is the light is striking the mirror and it's going right back along the same path, but when our eye projects it back, we see it pass through the center of curvature. That means that what we end up seeing is this image right here. So just by this ray diagram, without doing any of the math yet, other than, hey, I've got this focal length here, but just with this diagram and looking at the problem, we know that this image needs to be virtual, And we know it's virtual because this image is upright. Upright and virtual go together. We started with an arrow pointing upwards. Our arrow is in the end upwards. We have not inverted it or flipped its direction. So I know right off the bat that the image is virtual and it's upright. So hand in hand there. What we really need to figure out at this point is just where is that image? Where is it located? And if we wanted to do this, we need to start pulling out some of the math of the mirror equation. So we know that for the mirror equation, 1 over the object distance, and we're using DO here. Sometimes you'll see S's in places of D's, or if you're going really old school, you'll mind your P's and Q's. But right now we're just using D for some distance, how far away is the object, plus 1 over DI, the image distance, this is what we're looking for, equals 1 over the focal length. We know Fariah Jerry started this 20 centimeters away from the mirror. That is the object distance. We can just slot that in down here. So we end up getting that 1 over 20 centimeters plus 1 over DI equals 1 over the focal length, which, as we had before, was 2.5 centimeters. And this is where, if we're not careful, we can make a grave mistake. We know this focal length here, it's behind the mirror. That's negative. That's a negative focal length. Because of this, we need to remember to place that negative in there, or else everything is going to get weird. If we wanted to solve this out, we could add the 1 over negative 2.5 centimeters to each side. So we would just add 1 over negative 2. Excuse me, that is a negative number, so we're just adding it. We're just adding 1 over 2.5 to the other side. That makes these go away, but then we add over here 1 over 2.5, and we will subtract 1 over DI from each side. So what we get in the end is 1 over 20 centimeters plus 1 over 2.5 centimeters equals negative 1 over DI. Having that negative DI is helpful, especially because the left side is entirely positive, because this means that our DI is once again behind the mirror, and we know those values are still negative. So if we just want to solve this, easiest way to do this is just crunching in your calculator. I'm doing one step at a time. I like to take 1 divided by 20 and hit enter, get a value for that. I get 0.05. Technically my units here are 0.05 over centimeters, but I'm just going to ignore that for a second. Or rather, it's 0.05 over centimeters, excuse me. If I do the 1 divided by 2.5, I get 0.4 equals negative 1 over DI. If I add the 0.05 and 0.4 together, I get 0.45 equals negative 1 over DI. And the easiest thing here is to just flip both sides, take those reciprocals. So we end up seeing that 1 over 0.45, and this is nice because that centimeter was actually in the denominator, and then we flipped it up top, equals negative DI. And if we take 1 divided by 0.45, we end up finding that negative DI is 2.22 centimeters, which means if we just snag that negative and bump it over, DI equals negative 2.22, repeating, centimeters. So that's a quick way we can do that. We know that answer is correct. We want that negative distance for the image because we're behind the mirror here. So we have to have that negative number, those negative quantities. We were careful about our focal length, which was huge for this problem. They give us diameters, so doing that was important. And we kept in mind that, hey, that focal length was negative right here, that negative 2.5, because once again, it was behind the mirror. So just a few things to keep track of doing those problems. But with that, that problem's finished.